Thank you, Chairman. Today I'm going to give a talk about the barocaloric effect in spin crossover complex. And I'm going to talk on the behalf of my collaborators. I'm going to acknowledge them at the end. We know that our world energy demand is rising. We have been reading this in our papers in the introduction, but somehow by the energy agency, they have already realized that the energy needed to cool our system, our world is at the crucial level. And while writing some proposals, I have somehow found a paper from the Guardian newspaper, which they say that keeping cool makes us hot, which is a very nice introduction to say that we are going to really have a problem to cool our and we know that these are the problems. Thanks to Luis and Xavier to clearly define that made a basis. We have a problem about the cooling, and we all know that we need an alternative. We should do smarter to cool our cooling system, and Xavier also explained these ones very well. So that's I'm also skipping this one to the version of the magnetocaloric, barocaloric, elastocaloric, or mechanocaloric effects up to now. So we know that magnetocaloric is the superstar among all the caloric effects. However, some drawbacks it has, and I think the most important one is that there is a quantum mechanical size of limiting case for the magnetocaloric effect. So by the Clausius-Clapeyron relation, it says that you cannot go further with the magnetocaloric effect. So it is an important point that this 120 mu per gram, it's a limiting case, upper limit case for the magnetocaloric effect. We cannot go beyond. And the other problem is that for the magnetocaloric effect, the definition of the, we all have seen that they called giant magnetocaloric effect somehow, but the giant term is defined as 2 or 3 Kelvin for 2 Tesla. They called, or the papers, they are called giant magnetocaloric effect. But we will see that that is not the real case. We should update this definition because it is too much used in the papers, in the research papers. Besides, we know that we need high magnetic fields, and the materials are expensive. Magnetocaloric materials are expensive. On the other side, the application of the hydrostatic pressure is easier, and the materials are much more cheaper with respect to the magnetocaloric materials. And this is a film skin of this guy. Is a famous guy in the Turkey, and he's a detective in this film, and he solved the problem. He solved the case, and while dying, he is giving to his friends that you should change your perspective. So at this stage, I have read a paper from the Sandeman. He states that the mechanocalorical potential of the spin crossover compounds. So this paper changed my perspective, and in this paper he says that there is a very, very good potential of the spin crossover materials about the elastocaloric or barocaloric properties. So let me just briefly tell you the spin crossover compounds. This spin crossover terms that it is the change in the electronic spin state of the molecule that can be stimulated by external stimuli. This can be either temperature, this can be either pressure, this can be either magnetic field, and so also light. And up to date, these materials have been found since 1940 by Cambe and his co-workers, and these materials are work totally by the chemists, and it is very, very well known material, and they have, this low state and it has high state, and you can induce these states by the, external stimulus. And these materials are they have only a paramagnetic and diamagnetic transition. Their magnetic properties are not so well compared to our ferromagnetic materials. And up to date, most of the spin crossover compounds, they have very large hysteresis. They want these large hysteresis because they are using them as in displays and memory devices, because they want this low state and high state should be permanent. And they use these ones in the electrical and electroluminescent devices and to quench the light. But all these properties needs very high hysteresis. And this is the schematic for the how the spin transition takes place when you apply external stimuli. Let's say that you are in the high spin state, so somehow you are starting to encouraging the low state to take place, and at the final, with the enough pressure, you will reach the low state case. And this is also the energetic diagram for the with the applied pressure. As you increase the pressure, you are coming from the high spin state to the low spin state, and the pressure that means that pressure dominates the low spin state. And at that point, with the paper of the Sandeman, we have started with work on a project that is also sponsored by from our side, sponsored by the TÜBİTAK, and thanks to the Professor Luis Mañosa, he cooperated with us on this project. And the Baracaloric properties about the spin crossover materials, there is only 3 papers. Up to now, 2 of them was made with other researchers, and at the final we published a paper, and these are the results that we have published in this paper. The previous results, they have found it 7 Kelvin. Keep in mind that in the magnetocaloric case, 2 or 3 Kelvin was defined as giant, but at this stage they found it 8 Kelvin by von Ranke and et al. And similarly, the Volan in the Advanced Materials paper, they found very nice results. But all these results, they have hysteresis. But in this material, it is hard to say its name, because as a physicist, it is hard to tell their names for me. But this FBT material, we found it from the literature. It has very, very narrow hysteresis, just 1 Kelvin. And it has a abrupt transition at the 318 Kelvin. And we started to work on this material, and according to the XRD results, with and without the pressure, we have identified the unit cell parameters. And as you see, at this 318 Kelvin, we have an abrupt change for the volume change. And we have identified thermal expansion parameters and compressibility from these XRD results. I'm just skipping this part. We also made magnetic measurements. At magnetic measurements, according to magnetic measurements, we have only 1 Kelvin hysteresis. And that is very, very good point for us, because the hysteresis is very important. As Professor Mañosa said, that the hysteresis is very important about the cyclability, for the repressibility. And with this very narrow hysteresis, we are very expected very good results about this material for the barocaloric results. And later we made DSC measurements and specific heat measurements. According to the DSC measurements, we have a transition around 80 joule kilogram per Kelvin, joule per kilogram Kelvin. And in this transition, we have 2 components. One of them is the lattice component, the other one is the magnetic component. and we have calculated the magnetic component as 17 joule per kilogram Kelvin, and then we can find the lattice component as 63. And later then we started to make high pressure calorimetry studies in the University of Barcelona. And as you see, as we increase the pressure, the temperature shifted to higher temperatures. That means low state becomes dominant in this material, shifted to higher temperatures, and here we can see this shifting is according to the entropy, and this shift was calculated as 20 Kelvin per bar. Keeping in mind that the results from the Professor Luis Mañosa and Xavier Moya, this increase in the transition temperature is quite high. And we have also calculated this transition from the Clausius coeprime, and there the experimental and theoretical calculations are in line with. And according to the previous results, we built a phase diagram for this material, and as you see, we have very narrow pressure hysteresis, which is 65 bar for the pressure. So all these results are according to the old results, and as Professor Mañosa explained, we have we calculated or determined the entropy changes according to the pressure and the temperature. And then we have deduced our isothermal change corresponding to the first application and removal of the pressure. As you see, we have a giant temperature span, which is very good. And we also had the entropy change from the application or removal as 120 joule kilogram per Kelvin. According to our results, with a very low pressure, we can induce 6 Kelvin, and with the 6 kilobar, which is our upper limit, we have 35 Kelvin temperature change. Please keep in mind that in the giant magnetocaloric effect, it is only defined if you call it 2 or 3 Kelvin and 2 Tesla joules was called giant magnetocaloric. So I guess we should call this one supergiant, whatever. And these values are the largest among all reported barocaloric materials. And this is the change of temperature, adiabatic change of temperature according to the pressure and the temperature. And we also checked about the reversibility. As the previous speaker said, that the reversibility is very important thing for us. And according to the reversibility, the negligible hysteresis, because it is only 1 Kelvin, and the strong sensitivity for the transition, we have very, very good reversibility, because it we can say that it's almost full reversible on the whole temperature range. And we also calculated the refrigerant capacity. Sorry, I prepared in the keynote, but this one goes at that side. We checked the refrigerant capacity, and we also calculated the coefficient of the refrigerant performance as like that. And we checked that with the literature, and we found that these are the largest reporter for the giant and colossal caloric materials. And in order to compare the results with other materials, we have some good other results, but some of them, these stars, they are better, or these ones are better, but they are not reversible. For our material, we have very good shift of transition temperature. We have 120 joule kilogram Kelvin entropy change, Our temperature span is also very good, 50 Kelvin, and adiabatic temperature change is the best among the all caloric materials. And so, as a conclusion, we reported the barocaloric effect in this FPT material, and we found giant values for the isothermal change and adiabatic temperature, and the highest adiabatic temperature up to date in the literature. And we believe that these results are going to stimulate barocaloric properties, barocaloric effects observed in materials, also in spin crossover materials. And I believe that like Geschneider, what did with this gadolinium, silicium, germanium, this material will be a treat stone for the spin crossover materials. And I would like to thank my collaborators. We have published this paper in the Advanced Materials in the February. Professor Manyoza was the PI, principal investigator, is the head of this investigation, and we also have some collaborators in the Florida State University, and we have some collaborators in the Ankara University and China. I would like to thank also from the UPC, Professor Tamarit. I would like to thank all my collaborators, and I would like to thank also for the financial support from the TÜBİTAK and the other Mineco and Catalonia support from the DGU. Thank you for your attention.
Thank you very much for the interesting presentation.
As I know, people usually use so-called Gruneisen parameter to characterize caloric effects, but I think you don't use this terminology, huh?
Instead of it, instead of it, we have calculated the compressibility and thermal expansion parameter from the XRD results. That's why we use these parameters.
Okay, so let's have a coffee. 10 minutes.